All right, so in this section, we are going to talk about the derivative. First, we're going to talk about the conceptual idea of a derivative, and then we're going to actually go through the definition, the formal definition. And then once we go through the formal definition, we'll go through some examples using the formal definition. So there's two ways that you can look at a derivative, two different perspectives. One is geometrical and one is physical. So when we think of it as, we already kind of talked about the geometrical perspective in the very first section of this course. When we look at a curve, and I'll just use x squared as my example because we're all very comfortable with x squared. If I want to find a point on that line and I want to find the slope of the line that just touches that point right there on the curve. This is called the tangent line because it touches at one point. What we need to do is we need to use that point along with other points to find the slopes of these lines to get it closer and closer and closer until we're so close that the points are almost overlapping and we can make a really good estimate of what that slope is. The goal is to use the secant lines, which uses 2 points, and then make those 2 points get closer and closer and closer together. And that distance in the definition is called h. That's the distance between the 2 points. So that's where we have two equations in the definitions, and either one will work. But that's where this h comes in as the h gets smaller and smaller and smaller. So as the limit, as h approaches 0, we are finding the difference in the y's. This is my y2 minus my y1 over the difference in my x's, which is the distance between the two x's, which is our h. So that's this definition here, and this one's very similar. We're literally just using the point of interest and then plugging in other points here. And then we find the limit as these values that we plug in for x get closer and closer to a. So there's two equations you can use for the definition. Now that's the geometrical approach, as we're looking at it in terms of the slope of a tangent line. Now, the physical perspective is when you're looking at it as a rate of change. Okay, and if we're looking at it at just specifically one point, it's an instantaneous rate of change. When we're looking at the secant lines where we're using 2 points, we're finding the average rate of change between those 2 points. And then as those points get closer and closer and closer together, where they're almost overlapping, we can estimate the rate of change at that one instant. So let me erase this so we can unclutter. So we have these two equations on how we define the derivative. And I can't stress this enough. When we talk about the derivative, remember, the derivative represents the slope of the tangent line at a specific point on the graph. And if we're looking at it from the physical perspective, it's the rate of change at that specific instant. Okay, let's walk through the first example. Now you can use either one of these, it doesn't matter, but my preference is to use this one. I think it's a little bit easier. So if we want to find the derivative at an x value of 3, notice the notation for the derivative looks like this. So it's f, that's our function. This little slash up here where we would normally have an exponent, that's the symbol to represent that we're looking for the derivative. And then we can plug in a point here to indicate that we want to find the derivative at a specific point. So in this case, we want to find the derivative at x equals 3. So I'm going to use the first equation for the definition. in this case, in this example, the point of interest is 3. So that's our value of a. So I'm going to plug in everywhere I see a, I'm going to plug in 3. So I'm going to look for the slope of the line that touches the curve x squared at that one point x equals 3. So I'm going to find the limit as x approaches 3 of f of x, which is x squared, minus, if I plug in 3, I get f of 3 over x minus 3. And this is equal to the limit as x approaches 3 of x squared minus 9, because if I plug in 3 into my function, I get 9. And then this is all over x minus 3. Now we're going to use our tricks and our limit laws to break this down. I'm going to factor x squared minus 9 into x plus 3, x minus 3, all over x minus 3. I can cross this off. And then I'm going to finish down here because I'm running out of room. That's the limit as x approaches 3 of x plus 3. Now, when I plug in 3, using our limit laws and using direct substitution, I get 6. So the slope of the line, let me write this down. What this 6 means is the slope of the tangent line at x equals 3 on the curve x squared is 6. Okay, let's do the next example. I'm going to use the first equation in the definition, which is this. So I'm trying to find the slope of the secant lines as they get closer and closer and closer to x equals a. And the slope is the difference in the y's over the difference in the x's. Here's the difference in my y's. And here's the difference in my x's down here. Now, my a in this case is 2. That's my point of interest. I'm trying to find the derivative at x equals 2. So everywhere I have a, I'm going to plug in 2. So I'm going to take the limit as x approaches 2 of f of x, which in this case, f of x is the function 3x squared minus 4x plus 1. I'm going to subtract my value of f of a. If I plug in 2 into the function 3x squared minus 4x plus 1, I'm going to get 5. So I'm going to subtract 5 all over x minus 2. I'm going to carry on down here. When I clean this up and factor, I get the limit as x approaches 2 of x minus 2 times 3x plus 2 all over x minus 2. I can cross these off. So I'm going to get the limit as x approaches 2 of 3x plus 2. And now I can use direct substitution and the limit laws. And when I plug that in, I get 8. So what this means is on the curve, 3x squared minus 4x plus 1, on that curve at x equals 2, the slope of the tangent line is 8. Okay, now we're going to go on to the next example, and in this example we're going to take it one step further and actually find the equation of the tangent line. So just quickly, let's remind ourselves that this notation that we had before, this means the derivative at x equals 3 is 6. That's what this means. And conceptually, what this means is the slope of the tangent line at x equals 3 is 6. So if we're trying to find the line that just touches that curve at the point x equals 3, we already know what the slope is. It's 6. So here's our equation of any line, just in general. M is the slope and B is the y-intercept. We already know what the slope is. We just found it. The slope of the tangent line at x equals 3 is 6. So we can put that in for M. So I'm going to put in M is 6. Okay, now we have to plug in a point for x and y so we can find our value of B. Well, we want to make sure that we're picking a point on the tangent line, and we know that the point on the tangent line that touches the curve is x equals 3, and the corresponding y value would be 9, because when I plug 3 into the function, I get out 9. So this is what I'm going to use for my x and y to plug in to find my value of B. So I'm going to plug in 9 for y. I'm going to plug in 3 for x. And I'm going to figure out what B is. So B is going to be 9 minus 18, which is negative 9. So the equation of the tangent line at x equals 3 is going to be y equals 6x minus 9. I want to find another point on the line so I can graph it. So if I pick a point x is 2, I get 12 minus 9, which is positive 3. So that would be this point right here. That's as good as it's going to get, I think. Okay, so this is the tangent line at x equals 3. All right, let's look at the next example. Now this one we haven't already found the slope of the tangent line at x equals 2, so we have to do that first. If you look at this previous example, we already did find the slope at x equals 3 on that curve up here in the very first example. See, we did that already. So we could skip that step in this example here, where we're trying to find the equation of the line tangent to the graph x squared at x equals 3. But this one here, this next example, we still have to find the slope. We haven't done that in a previous example. So the first step, if we want to find the equation of the line tangent to that graph, f of x, at x equals 2, we need to find the derivative at 2. And that will give us the slope of the tangent line. So first, we're going to find, so in order to find the slope, which is the derivative at x equals 2, we're going to use this formula. The limit as x approaches 2 of f of x minus f of 2 over x minus 2. So f of x is 1 over x. F of 2 is 1/2. So in the numerator, I have 1 over x minus 1/2. And the denominator, I have x minus 2. Now I can't do direct substitution here and use limit laws at this point because I would have 0 in the denominator. So I have to use one of our algebraic techniques to rearrange this algebraically so that I can do direct substitution and use limit laws. So what I'm going to do here is I'm going to clear the complex fraction by multiplying both the top and the bottom by 2x. Because if I look at my mini fractions, the 1 over x and the 1/2, and then I'll write this as a fraction 2 to be consistent, the x over 1 and the minus 2 over 1. If I look at those smaller fractions, my common denominator is going to be 2x. So that's why I'm choosing to multiply everything by 2x on the top and on the bottom. So I'm going to take the limit as x goes to 2, and when I multiply everything by 2x on the top and the bottom, I'm going to be left with 2 minus x over 2x times x minus 2. Now if we continue to simplify this, I can rearrange the top by factoring out a -1, and that way I can write the top as -1 times x minus 2 over 2x times x minus 2. And the reason why I pulled out that -1 from the numerator is so that now I have x minus 2 on the top and the bottom, and I can get rid of those. So now I'm left with the limit as x approaches 2 of -1 over 2x. Now I can use direct substitution and the limit laws, and when I take the limit as x approaches 2 of -1 over 2x, I get -1/4. So that tells me that the slope of the tangent line at x equals 2 is -1/4. So this is the slope of the tangent line at x equals 2. So now if we want to keep going and actually find the equation of the line, here's my general formula of a line. I'm going to plug in -1/4 for my m, because that's the slope. And now I need to plug in something for x and y. So when x is 2, my corresponding y value is going to be 1/2. Because the function is 1 over x, so when I plug in 2, I get 1/2. So there's the point that I'm going to use. Make sure that you're picking a point that is actually on the tangent line, or this isn't going to work. So it's a really good habit to get in to just use that point of interest every time, because you know that will be on your tangent line. So I'm going to plug in 1/2 for y, -1/4 times 2 plus b. So when I multiply the -1/4 times the 2, that gives me -1/2. And when I add 1/2 to both sides, that gives me b is equal to 1. So then my formula is going to be, so my equation for the tangent line at x equals 2 is going to be y equals -1/4 x plus 1. And we can check it on the graph. If I graph the line -1/4 x plus 1, here's my y-intercept at 1. Picking another point, such as the x-intercept, I would get 4, 0. Now if I can draw this with a steady hand, it's going to pass through these 2 points, just touch at the point at x equals 2, right here, and keep going. In this next example, we have to find the equation of the tangent line to the graph of the square root of x at x equals 4. So the first thing we need to do is find the derivative at x equals 4, because that will give us the slope of the tangent line at x equals 4. So we're going to use the definition, the limit as x approaches 4 of f of x minus f of 4 over x minus 4. Now if I put in f of x, that's the square root of x, minus, if I plug 4 into the function, I get the square root of 4, which is 2, all over x minus 4. Now I'm going to use the conjugate trick because we can't at this point use direct substitution in limit laws. So I'm going to multiply the top and the bottom by the square root of x plus 2 over the square root of x plus 2. And that will give me the limit as x approaches 4 of x minus 4 over x minus 4 times the square root of x plus 2. Now we have a factor that's the same on the top and the bottom, so I can cross off the x minus 4. So I've got the limit as x approaches 4 now of 1 over the square root of x plus 2. Now I can use direct substitution and the limit laws, and when I do that, I get 1/4. So this is the slope of the tangent line. At x equals 4. So here's my general equation of a line. I'm going to plug in 1/4 for my slope. And now I need to plug in a point, and we want to make sure we're picking a point that's on the tangent line. So we're going to use our point of interest, which is 4 for x, and when I plug in 4 to the function, my corresponding y value would be 2. So I'm going to plug in 2 for y, 4 for x, and I'm going to get that b is 1. So now I've got the line y equals 1/4 x plus 1. So my y-intercept is 1, so that's right here. And I have a point 4, 2. If you want, you can pick one more point to plug in. Let's say we plug in 8. That's going to give us that y is 3. So that'll be right here. And here is our tangent line that just touches at x equals 4. Now let's talk about velocity and how that's related to the derivative. So now that we can evaluate a derivative, we know that the derivative is the limit of the slopes of the secant lines as those 2 points get closer and closer and closer together until we have the slope of the tangent line. So if we consider a function s of t, we'll call it the position function. So this tells us the position of some kind of object moving, and t represents time. So in other words, if I put in the time is 6 seconds or 3 minutes or whatever into the function, whatever those units are, we're going to get out the position of the function. And that's what that function does. If we consider that position function, we have some kind of curve. If I find the slope of the secant line between 2 points on that function, what we're really doing is finding the average rate of change over that time interval from one point to another. And when we're talking about average rate of change of a position over time, what we're really doing is talking about the velocity or the speed, right? If I'm changing my position, which would be some kind of distance, miles, meters, feet, and then we're talking about changing it over a period of time, that would be feet, seconds, minutes. We're talking about velocity, right? Feet per second, miles per hour. So if I want to find the instantaneous velocity, meaning the velocity that you're traveling at a certain instant, what we're going to do is take the derivative and find the slope of the tangent line at that one point. That would be the instantaneous rate of change. So we're going to say that the instantaneous velocity is going to be the derivative of the position function at a particular time. So if we want to find the instantaneous velocity at t equals a, then the instantaneous velocity is going to be the derivative of the position function at a. And we'll call this v of t, the velocity. All right, so let's move on to our next example. We have a rock is dropped from a height of 64 feet. Its height above the ground at time t seconds later is given by the position function negative 16t squared plus 64 on the interval from 0 to 2 seconds. And the question is asking us to find the instantaneous velocity at 1 second after it's dropped. So the instantaneous velocity means we need to find the derivative of the position function at t equals 1 second. So we're trying to find this. So we're going to use the definition of the derivative to find the limit as t goes to 0. Now we're using t's instead of x's here because we're talking about time, and that's our independent variable. Our position function minus our position function at 1 over t minus 1. Whoops, this should be a 1. Okay, now I'm going to put in the position function. The position function is negative 16t squared plus 64, and I'm going to subtract s of 1. Now, if I plug in 1 into the position function, I'm going to get 48, and that's all over t minus 1. I'm going to continue down here at the bottom since I'm running out of room. The limit as t approaches 1. Now, if I clean up the top, that gives me a negative 16t squared plus 16 over t minus 1. On the top, I can factor out a negative 16, and then I'm left with t squared minus 1, which can be additionally broken down into t minus 1, t plus 1. So I've completely factored the top, and I'm left with t minus 1 in the denominator. Now, I have t minus 1 over t minus 1. I can get rid of that and clean this up a little bit more and say the limit as t approaches 1 of negative 16 times t plus 1. All right, so now I can use direct substitution in the limit laws, and I have the limit as t approaches 1 of negative 16 times 1 plus 1, so that's going to give me a negative 32, and our units here are going to be feet per second. Okay, now the 32 feet per second here represents the speed. And what makes velocity different than speed is that velocity also indicates a direction. And this negative, in this case, indicates the direction of the object. Okay, now in this example, I'm going to apply the same concept that we applied in the previous problem with the average rate of change of velocity versus the instantaneous velocity. I'm going to do that here with temperature, where we could look at temperature over an interval of time, which would be the average change in the temperature, or if we want to look at it at a specific instant, that would be the instantaneous rate of change of the temperature. And when we want to talk about the instantaneous rate of change, we want to use the derivative. So in this example, it says a homeowner sets the thermostat so that the temperature in the house begins to drop from 70 degrees Fahrenheit at 9 p.m. and reaches a low of 60 degrees during the night and then rises back up to 70 degrees by 7 a.m. the next morning. Suppose that the temperature in the house is given by this function. So we have a temperature function. The capital T is the name of the function, and the lowercase t represents time. It says in the problem here that T represents the number of hours past 9 p.m. And we want to find the instantaneous rate of change of the temperature at midnight. So we want to find the derivative of the temperature, but we want to specifically find it at T equals 3. Now, why didn't I pick 12? 12 is midnight. Look at the way that the value of T is defined. It says that T lies between 0 and 10, so we can't use 12. And then it also says that T is the number of hours after 9 p.m. So if T represents the number of hours that are after 9 p.m., 3 hours have passed after 9 p.m. if you're talking about midnight. So we want to set T to be 3 hours. So what we're looking for is the derivative at 3. So we're going to use the definition. We're going to find the limit as T approaches 3 of the function minus the value of the temperature at 3 over T minus 3. And that's going to give us the limit as T approaches 3. I'm going to plug in my function, which is 0.4 T squared minus 4T plus 70. And then I have to subtract the value of the function at T equals 3, which would be 61.6. And that's still over T minus 3. Now, when we clean this up and we simplify the top, we're going to get the limit as T approaches 3 of 0.4 T squared minus 4T plus 8.4. Now, I can't use direct substitution yet. And the limit laws, whoops, I forgot my T minus 3 down here. I can't use direct substitution or limit laws yet because we have that T minus 3 in the denominator. So I want to do some manipulation here to factor and see if I can get rid of that T minus 3 in the denominator. So I'm going to pull out a 0.4 from this function, and I'm going to get, and what I'm going to be left with is T squared minus 10T and then plus 21. And that's all going to be over T minus 3. I'm going to continue trying to break this down and factor. So I have 0.4, and then I can factor the T squared minus 10T plus 21 into T minus 3 and T minus 7 all over T minus 3. I can cross off the factors they have in common, so I can get rid of T minus 3. What I'm left with is the limit as T approaches 3 of 0.4 times T minus 7. Now that I've gotten rid of that denominator, I can use direct substitution and limit laws. So if I take the limit as T goes to 3, I'm going to get negative 1.6. And this is in degrees Fahrenheit, and it's per hour. T is in hours, and the value of the function is in degrees Fahrenheit. So this means it's changing 1.6 degrees Fahrenheit per hour. And the negative just indicates that. Okay, so let's go on to the next example, which is our last example in this lesson. We're going to do rate of change of profit. So the question reads, a toy company can sell X electronic gaming systems at a price P equals negative 0.01x plus $400 per gaming system. The cost of manufacturing X systems is given by this cost function here, which is 100x plus $10,000. Find the rate of change of profit when 10,000 games are produced. And then we also need to additionally answer the question, should the toy company increase or decrease production? So we want to find a profit function because we're not given the profit function. And then we want to find the derivative of that profit function at an instant, and we want to find what that rate of change of the profit is at 10,000 games. So to find a profit function, we need the revenue function minus a cost function. We're given the cost function in the problem. We are not given the revenue function. So, but we are given enough information to figure it out. We're given the price, which is that P equals negative 0.01x plus 400. And if we want to find the revenue, that's how much money we're taking in when something is sold. We want to take the price of the item times the number of items. So, for example, if I was selling radios for $100, and I sold 10 radios, if I wanted to figure out my revenue, I would take 100 times 10. And that would tell me how much money I would take in. But then I have to subtract off my cost to find the profit. So we need to take the price times the number of games that we're selling for the revenue. So that would be the price, which is negative 0.01x plus 400 times x. So this is the price times the number of games. That's going to give us our revenue. And then we subtract the cost function, which is 100x plus 10,000. Now, when we clean this up and we distribute the x and we distribute the negative in front of the cost function, we're going to get negative 0.01 x squared plus 300x minus 10,000. So here is our profit function. Now we need to find the derivative of the profit at 10,000. Now let's use the definition of a derivative, which would be the limit as x approaches 10,000 games of the profit function, which is negative 0.01x squared plus 300x minus 10,000. We want to subtract off p of 10,000. And when you plug in p of 10,000, you're going to get 199,000. Okay, and that's all over x minus 10,000. Now, when we clean this up a little bit, I'm going to get in the numerator negative 0.01x squared plus 300x. And then when I combine the minus 10,000 and then this minus 1,990,000, that's going to give me a minus 2 million. And that's all over x minus 10,000. Now we're going to factor this because I can't use direct substitution just yet. And although the numbers are big and cumbersome, we're going to factor this just like we would any other polynomial. I'm going to first pull out that negative 0.01 to make it a little bit easier. So I'm going to be left with x squared minus 30,000 x minus, that would be 200 million. If I counted my zeros correctly. And that's all over x minus 10,000. All right, now we're going to factor the rest of that, we're left with minus 0.01. Whoops, I forgot to change this to a plus. So that should be plus 200 million. Now when I factor, I'm going to get x minus 10,000, and then I'm going to get x minus 20,000. So I can cross off the x minus 10,000s, and I'm left with the limit as x approaches 10,000 of negative 0.01 times x minus 20,000. If I plug in 10,000, I'm going to get inside the parentheses negative 10,000. And then when I multiply it by the negative 0.01, that's going to give me $100 profit. And this is per game. Now, because the rate of change of the profit is positive, and because the profit itself is positive at 10,000 games, it's a good idea for the company to increase production